Hello, I am Bruno E from MIN Paris. I will present our paper on Autoencoder-based background reconstruction and foreground segmentation with background noise estimation. Our goal is to take a video as input and produce two outputs. First, we reconstruct the background of each frame appearing in the video without the moving objects or persons appearing on the frame. Second, we also perform for each frame a segmentation of the foreground objects from the background. State-of-the-art background reconstruction methods are based on robust PCA, which is a linear method implementing two inductive priors. First, we expect that various background frames lie on a low-dimensional manifold. Second, the foreground object image should be spaced in the video. Our model has a structure similar to the deep PBM model by Arnaud Description, which also uses an autoencoder instead of linear methods to enforce the low-rank condition on the background manifold. The model is based on a convolutional autoencoder. During trainings, the autoencoder takes as input a video frame and outputs two images. First, a background reconstruction, and second, a pixel-wise prediction of the L1 loss associated to the background reconstruction. This prediction allows to estimate the level of background noise on this pixel. The reconstruction loss associated to the background reconstruction is the sum of the L1 losses associated to each pixel, weighted by bootstrap weights, which give a low weight to the L1 loss if it is very high, which can be caused by the presence of a foreground object on this pixel. The loss associated to the background noise estimation is computed as the difference between the true L1 loss and the predicted L1 loss, weighted by the same bootstrap weights. During inference, we get directly the background reconstruction from the autoencoder. In order to build the foreground segmentation mask, we perform a thresholding of the L1 error map using a pixel-wise threshold, which is computed as a weighted sum of the average illumination of the reconstructed background and the predicted level of background noise at this pixel. A morphological post-processing is then performed to get the final segmentation mask. In order to take into account the background complexity, we first initialize the autoencoder with a low number of parameters and perform only 2000 training iterations. We then check whether this partially trained model provides a good reconstruction of the input image. If it is the case, we conclude that the video shows a simple fixed background and finish the training after 500 steps. If this is not the case, we conclude that the video shows a complex or moving background and restart the training with the model having more parameters and for a total of 24,000 iterations instead of 2,500. We tested the proposed model on the CDnet 2014 dataset, where it improves on average upon the state-of-the-art compared to other fully unsupervised models. One remarks that the model leads to a significant improvement on categories involving moving cameras, for example the point-tilt zoom category. We also improve on the state-of-the-art on the LASIESTA dataset, although this dataset contains very short video sequences. Let's have a look at some examples of background reconstruction and foreground segmentation. The first video shows a very high level of turbulence. The second video shows a dynamic background with moving grass, moving clouds, and substantial illumination change. Let's now have a look at some videos involving substantial camera movements. The first video involves some zoom, and the second video is taken from a moving camera. We have also tested the proposed model on three identical image datasets which are not video sequences. The various images of each dataset show different backgrounds, but the proposed model is able to perform background reconstruction of the datasets because it does not require any temporal information and only relies on the inductive prior that the background frames should lie on a low-dimensional manifold. The code of the proposed model is available on GitHub. Thank you for listening.